Uncertainty in future energy prices and environmental implications are prompting building owners to use energy resources more efficiently. The National Institute of Standards and Technology estimates that air infiltration through leaky envelopes is responsible for 33% of heating energy use in U.S. office buildings. The U.S. Army Corps, other federal government entities, and even the state of Washington have established requirements for whole building air leakage testing. As a result, there's been a dramatic increase in the demand for large building blower door air leakage testing. Until recently, blower door testing was mainly performed on small residential and non-residential structures. Advances in equipment and software have made it much easier to conduct multiple fan blower door tests on large buildings. Check out this walkthrough. The number of fans needed for an air barrier performance test is determined by the referenced air tightness specification or standard. Identifying fan locations that will provide effective pressure distribution is a necessary part of the setup. There are many details and logistics to consider. Proper preparation is crucial. It is efficient to pack everything needed for a 3-fan system in one duffel bag, something about the size of a black duct blaster bag. This method saves time at the setup and teardown stages. It is helpful to have access to carts to move equipment from the staging area to the setup area. Blower door frames need to be installed securely. Equipment popping out of place during a test can extend the time required to test and possibly damage fans. Fans, speed controllers, gauges, tubing, and cables are installed next. When running extension cords, make sure each fan is on a separate circuit so that electric breakers are not accidentally tripped. The setup for a large building test is similar to those conducted in a house, just scaled up. Coordination with building management is key, as access to mechanical systems is necessary, and occupants can be affected when they are turned off. Bring a bag of wedges to prop open interior doors. Rooms along outside walls need to be left open so that all parts of the building are at the same pressure. 5 to 50% of building leakage can occur through intentional mechanical openings. Most test protocols require intentional openings within the test boundary to be sealed to a specified level. Sealing and unsealing these openings is one of the most labor-intensive and time-consuming parts of the test. Tarps, held in place by large hoods, and large garbage bags installed over rooftop ventilators that use 2-foot-wide carpet protector tape are some methods used to speed up the sealing process. It is good practice to measure air tightness with the building sealed and unsealed, marking the periods for both. The Energy Conservatory's new TechLog software allows you to control all of the fans from a central computer using one slide bar. Cat5 cable is used to connect DG700 pressure gauges to the computer. The software recognizes each gauge's serial number, allowing each pressure channel to be identified. A worksheet is used to gather information about the DG700 configurations, and that information is transferred to the software. While the software graphs the building pressures and the fan flows, periods of record are marked at predetermined building pressures. Typically, buildings are tested under both positive and negative pressures, so the test results page will show testing for both as well as the combined results. A report can be generated from these results. While the blower door test measures the building tightness, an air leakage investigation is necessary for determining where the air leakage is and how it can be sealed. Test findings also provide evidence for how air leakage can be reduced in new construction. Properly designed and tested type buildings will be more comfortable, durable, and affordable to operate. This test was designed and implemented as a collaboration between the Center for Energy and Environment and the Energy Conservatory, and funded by the Minnesota Division of Energy Resources.